Hello everyone. The title of this video is Graphing Logarithmic Functions. So in this video I'm going to be going over examples taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 6.4, called Graphs of Logarithmic Functions, and I'm under the heading Graphing Logarithmic Functions. Alright, so each example I do in this video will be either an example from the reading or one of the try it problems from the reading, or one of the exercises at the end of the section related to this particular objective. Alright, so I'm also going to be doing graphing logarithmic functions with transformations of logarithmic functions in this video. Alright, so before we get into graphing transformations, I want to talk about those basic logarithmic functions, which I have brought up in the earlier video from this section on finding the domain of a logarithmic function. So this is the same page I had in that video. Alright, we're looking at the graphs of basic logarithmic functions, and then every function besides these will be some sort of transformation of this. Alright, some transformed version of this. So your basic or your parent logarithmic function looks like this: y equals, the log base b of x. And if the base is bigger than 1, it's an increasing function. And some of the key points are 1 over b, comma negative 1, 1 comma 0, and b comma 1. Those are like the key points I'm going to be working with. For the most part, I'll just be finding 2 points. Again, in that last video on finding the domain of logarithmic functions, I pointed out how you really only need to know 2 points on the graph and where the asymptote is to be able to make a rough sketch of a logarithmic function. But we'll see that throughout this video as well. And the domain is only positive numbers. You can only have a positive number inside a logarithm. We saw that last video as well. The range for any logarithmic function is all real numbers. There's a vertical asymptote for these basic functions at the y-axis, right? The line x equals 0. See how the graph approaches the y-axis but doesn't actually touch it. Right, the domain is only positive numbers. And this asymptote will be moved, if you do some sort of horizontal shift. Right, if you do a horizontal shift left or right, the asymptote will move as well. And then if the base was less than 1, you had a decreasing function, but you still have those same 3 key points. You still have b comma 1, 1 comma 0, and then 1 over b, the reciprocal of b, comma negative 1. Right? Those 3 key points are still on there. All right, same domain, all positives, same range, all reals, same vertical asymptote of the y-axis, or x equals 0, but it is a decreasing function when the base is less than 1 for these basic logarithmic functions. Okay, so if you got these down, you got these in your head, the first couple examples I'll do, we're going to look at some of these basic ones where you're just doing log with some base of x. And then after a few of those examples, we'll look at some transformed versions and graph those as well. All right, so my first example is a basic logarithmic function with a base that's bigger than 1. Right? This is f of x equals the logarithm base 5 of x. And off to the side here, I'll just make a little table. And basically, what I want here I want to plug in, powers of 5, right? If this is base 5, I want the number inside the logarithm to be a power of 5, 1, 5, 25, or 1/5, 1/25, etc., so that the output's a nice integer, a nice, easy for me to take. Now, as with the last video, I'll say here again, the domain is, x has to be some positive number, some number greater than 0. The range is going to be all real numbers for all of these logarithmic functions. And once you have the domain set up, the asymptotes, the vertical asymptotes, should also be easy to tell. If I can only plug in numbers greater than 0, then x equals 0 is going to be where the asymptote's at. Alright, the y-axis. And if you have graph paper, that'll make this maybe a little easier. But here's the y-axis. I'll make this put some dashes on this. Right, this is an asymptote. Right, there's x equals 0. The graph will not be touching that line. And then I'm just going to plug in, 1. The log base 5 of 1 is 0. Right, 1, 0 is on the graph. 5 is a power of 5. The log base 5 of 5 would be 1. Right, 5 to the 1 power is 5. So there's 5, 1 is also on the graph. And really that should be enough. 2 points on the graph just to know if it's increasing or decreasing. And the asymptote. Those should be enough to make a rough sketch by hand, but I'll plug in some other points. How about 1/5? The log base 5 of 1/5 would be -1. Right, so 1/5 would be around here. Right? And then -1 for the output. And what you're going to notice is that, if I plug in 25, I'll get 2, and plug in 125, I'll get 3. So it's very slowly increasing. And then you plug in 1/25, you'd get -2, and then 1/125, you get -3. The closer to 0 I get on the right side here, the bigger negative, the lower the output gets. But having a few points in and the asymptote should be enough to make a rough sketch of the graph, and I should probably do this in a different color so it doesn't look like the asymptote. And here we go, right? And again, it's going to approach the asymptote but not actually touch it, go down forever like that. And then it's going up forever to the right, but just very slowly. And there's your graph. And notice that, basic logarithmic function, the base is bigger than 1, and we see here an increasing function. Right? As you go to the right, the graph is going up. The output's increasing. Right, and that's it. And if you want to look at a better picture, go to that Desmos website. It's a free online graphing calculator at desmos.com. And I put in, f of x equals log base 5 of x. And, the picture looks similar to what I had drawn. Right, you see you got 1, 0, you got 5, 1 here somewhere. There's 5, 1. Should have 1/5, -1, and you can make a little table if you want. Now notice that for values less than 0 or equal to 0, the output's undefined, right? Because you can only have positive numbers inside logarithms. But if I put in 1/5, see the output's -1. Put in 1/25, the output's -2. Right, put in 5, the output's 1. Put in 25, the output's 2. Put in 125, the output's 3. Right? Nice powers of 5 I plug in, and I get some nice integer outputs. Alright, good. So my hand drawing wasn't terrible. Alright, the next example is another one of those basic logarithmic functions, and then after this example we'll start getting into transformed versions. Alright, so there's y equals f of x equals, the logarithm base, the base this time is not 5, is 1/5 of x, which is less than 1, right? The base is less than 1. So once again, and I'll do this for every single problem. The domain, x, there's only x inside, so x has to be some number greater than 0. 0 to infinity, not including 0. Only positive numbers can be plugged in here. The range is always going to be all real numbers. And the asymptote, and I'll just put ASYM for asymptote, is going to be x equals 0 again. So this time, again, I'll do a little dash on the y-axis so you know it's an asymptote. Right? Here's x equals 0. Now again, 1, 0. Right? 1 zeros on this graph. The log base anything of 1 will be 0. But then 1/5, say this is 1/5. The log base a fifth would be 1, right? 1/5 to the first power is 1/5. And then plug in 5. 1/5 to the -1 is 5. So if I plug in 5, I get an output of -1. And then you can do other points. If I plug in 1/25, I'd get 2. If I plug in 1/125, I get 3. The closer to 0 you get, the higher the output is, and the further away you get, the lower it is. Right? This is a decreasing function. Right, looking something like this. Approaching the asymptote, but not actually touching it. Right? Something like that. And again, this is going down forever, but just very, very slowly. And once again, better picture on Desmos. Just change this base 5 to a base of 1/5. Oops. Log base 1/5. Alright, I gotta put that in parentheses, I guess. Alright, come on now. Come on. This is to get rid of the whole thing. Log base. Alright, you know what? I'll just make it the decimal then. Looks like the fraction bases are hard to enter. 0.2. If you can figure out how to enter a fraction base, please let me know. Alright, so 0.2. And then, yeah, see now all these are, 1/5 has an output of 1. 1/25 has an output of 2. 5 has an output of -1. 25 has an output of -2. And it's a decreasing function, like I had drawn. Great. Alright, so now we start getting into functions that are not the basic logs, but we can very easily get a transformation, a transform version. So number 3 here, f of x equals the log base 3 of x minus 2. So I'm going to graph this in 2 different ways. One is with transformations, from starting with one of the basic logs and then moving to this. So with transformations, we would start with y equals the log base 3 of just x, which would look like this. And I'll graph this over here, and then we'll transform it. Now, of course, the y-axis will be the asymptote for log base 3 of x. It's going to have 1, 0. It's going to have 3, 1. Right, the log base 3 of 3 is 1. It would have 1/3 -1, but this is all I'm going to need right now. Just know that these 2 points are on it, and it's got the y-axis as an asymptote, right? So here's the log base 3 of x in this color, right, in orange. And then all I would need to do to get this function to look like that one is replace x with x minus 2. And if I replace x with x minus 2, that would shift to the right 2 units. And I'm assuming you remember your transformations. So we have y equals log base 3 of, and then x is replaced by x minus 2. Well, if I shift this to the right 2 units, then instead of x equals 0 being the vertical asymptote, now it's at x equals 2. I'll make a dotted line here at x equals 2 for the asymptote. And then 1, 0 moves to the right 2 units to be 3, 0. And then 3, 1 moves to the right 2 units to be 5, 1. And it's the same picture, just everything shifted to the right 2 units. So that increasing function, but this time, the asymptote's at x equals 2. And there's the graph that they wanted, right? This is the graph that they wanted. Right. Now there was only one transformation going on there, so this is pretty simple. But if there's multiple transformations, right, I'll be doing a bunch of this moving around, and I don't really particularly care for doing that. I mean, when you're first learning transformations, fine, just to get used to the transformations. But I'll tell you right now, and I've mentioned this out loud, and I did this in the last video. The way I prefer graphing logarithmic functions is, find the asymptote in 2 points, and that should be enough to make a rough sketch. All right, find the asymptote in 2 points. All right, so remember how to find the asymptote is by, I'll do the same thing where I'm going domain, range, asymptote. If you know the domain, you know the asymptote. Remember the expression inside the logarithm, the number inside a logarithm must be positive. Right, so this x minus 2 must be greater than 0. Meaning that x must be greater than 2, right? So the domain of this function is all numbers greater than 2, right? So from 2 to infinity, not including 2. Range is all real numbers, as usual, for these logarithmic functions. And if you know the domain, you know the asymptote, right? If I can only plug in numbers greater than 2, then there's going to be a wall at x equals 2, an asymptote at x equals 2. Alright, so I do that, on my graph over here I make an asymptote at x equals 2, vertical asymptote. And then I just need 2 points. Now again, what I would like in here, since it's log base 3, I'd like to have powers of 3 inside the logarithm. Now powers of 3 would be like, 1/9, 1/3, 1, 3, 9, etc. And like I've been doing, I think the easiest 2 to get are, 3 to the 0, 3 to the 1. The 0th power and the first power, 1 and 3. If I plug in 3 for x, I'd get, 1 inside here, right? The log base 3 of 1, which would be 0. So 3, 0 is on the graph. And if I were to plug in, so that took care of 1. Now say I want 3 inside, I'd have to plug in 5 for x, right? 5 minus 2 is 3. And if I plug in 5 for x, you get the log base 3 of 3, which is 1. So the point 5, 1 would be on the graph. And you could do other points, try to get other powers of 3 inside the log, and then do the output calculation. But once you have 2 points and the asymptote, you should be able to make a rough sketch of the, knowing what logarithmic functions look like. Looks like something like that, which is kind of like what I had at the end here, right? See this graph up here, compared to the graph I made down here, it's basically the same thing. It is the same thing, all right? And, we can go to the Desmos site if you want. I'll do it for this one. Right? We have log base 3 of x minus 2. And you see the asymptote at x equals 2. Now, you could put x equals 2 in there, make it a dashed line, but and here's 3, 0, there's 5, 1, just like on my graph. Right? And it's an increasing function and all that. Right? So I personally, when I'm trying to do quick graphs of logarithmic functions, I like to state the domain, range, asymptote, and then find a couple points using the powers of the base as a guide. And once you know a couple points and the asymptote where they're located, and you know how the logarithmic functions look, or at least you should by now, you should be able to make then a pretty rough sketch by hand. Alright, so I'm going to do that here. Also, the asymptote in 2 points method. f of x equals the log base 3 again of x plus 4. So this would just be, if you were doing transformations, this is just the log base 3 of x, but move to the left 4, right, because x is replaced by x plus 4. But, I'm not doing all that. First thing I notice is that, again, I want to state the domain. X plus 4 needs to be positive, right? So x plus 4 needs to be greater than 0, meaning that x needs to be greater than negative 4. Right, so the domain of this function is everything greater than negative 4. So that's from negative 4 to infinity, but not including negative 4. All right, the range is all real numbers. And of course, the asymptote then would be at x equals negative 4. All right, so I go to make a graph. Here's negative 1, 2, 3, 4. There's where the vertical asymptote is going to be. And then I just start plugging in values so that I get powers of 3 in the input. Now the easiest power of any number is 1. If I plug in negative 3 for x, the output, that'll be 1 inside. Negative 3 plus 4 is 1. And then the log of 1 is 0. So negative 3, 0 is on this graph. Negative 3, 0. And then if I plug in negative 1 for x, right, negative 1, you'll have 3 in here. The log base 3 of 3 is 1. So negative 1, 1 would also be on this graph. And now that I have 2 points and the asymptote, I should be able to make a rough sketch of the graph. All right, it looks like it's an increasing function, like that. All right. Okay. Again, it should be that quick once you know a couple points in the asymptote. And I'm going to continue to do this. And I'll leave it to you to go to Desmos and check your work. Alright, so example 5. Alright, so this is f of x equals the log base 3 of x again. But then this time there's a minus 2 afterwards, outside. So remember what that does. If you were doing transformations, that would shift the graph of the log base 3 of x down 2 units. Alright. But again, I'm going to go through the same procedure I've been going through. The domain of this function is, x has to be greater than 0. The range is all real numbers. This is always the case for these logarithmic functions. And the asymptote is going to be the y-axis. It's going to be x equals 0. So again, I'll make the y-axis, put some dashes on it, so you know that that's the asymptote. And then plot a couple points. Now if I plug in 1, there's a log base 3 of 1 is 0, but then don't forget the minus 2. 0 minus 2 is negative 2. Right? So 1, negative 2 is on the graph. And then plug in 3. Log base 3 of 3 is 1. Minus 2 is negative 1. So 3, negative 1 is also on the graph. So it's an increasing function, right, with an asymptote at the y-axis. Looking something like this. Something like that. Right. And again, if you want to test it out, look on Desmos, do all that. Or go do transformations, do the graph the log base 3 of x and then move it down 2. You'll get this graph here. Alright, next. So this time I have the log, f of x equals the log base 2 of x, pay attention to the base, plus 2. So this should just move the graph of the log base 2 of x up 2 units, right, the plus 2 after. But again, I'm going to go through the same procedure I've been going through. The domain is only positives, it's just x in there, right, so x has to be greater than 0. Range is all real numbers. And the asymptote is still at the y-axis, right? Still at x equals 0. So again, here's asymptote, x equals 0. Plot some points. Now here I want to plug in powers of 2. Now 1 is a power of anything, so plug in 1. 2 to the 0 is 1, so this is 0. Plus 2 is 2, right? If I plug in 1, the output's going to be 2. Right, 1, 2 is on the graph. And then powers of 2, plug in 2. The log base 2 of 2 is 1. 1 plus 2 is 3. And so if I plug in 2, I get an output of 3. And then just based on this, it looks like it's an increasing function. It's going up as you move to the right, and it has the y-axis as an asymptote. Right, so something like this. All right, again, once you have a couple points, and you can plot other points if you wish. You can plot other points. If I plugged in a half, the log base 2 of a half would be -1 plus 2 would be +1. Right, 1/2 comma 1 should be on this. Right, this should be 1/2 comma 1. I mean, you could plug other points in too, just to get a little better idea of the graph. But once you know 2 points in the asymptote, you should be able to make a rough sketch of any logarithmic function. All right, next example. All right, so far and we're still sticking to just one transformation here. We have f of x equals 2 times the log base 4 of x. So if you want to do transformations, graph the log base 4 of x and then multiply all the y coordinates by 2, right? That would be a vertical stretch by a factor of 2. Alright, but again, I'm going through the same procedure as all the others. The domain is just, it's just x in there, so it's just positive numbers. Range is all real numbers for all of these. The asymptote is x equals 0. So again, the y-axis is an asymptote here. And then this time I'm plugging in powers of 4, right, for x. So log base 4 of 1, I'm going to plug in 1, I'll plug in 1 and 4. Right. Now if I plug in 1, this is going to be 0 times 2 is still 0. So 1, 0 is still on the graph. If I plug in 4, right, the log base 4 of 4 is 1. But then don't forget the times 2 would be 2. So if I plug in 4, the output would be 2. You get 4, 2. And again, I'm seeing there's an increasing function here with the y-axis as a vertical asymptote. Right? So something like that is this graph. Right. And again, you can plot other points if you want. All right, like if I plugged in 1/4, 1/4, I'd get -2 as an output. All right, and you can plug in other powers of 4 if you wish, get more outputs, get more points, but 2 points in an asymptote should be enough to make a rough hand drawing. All right, so example 8. F of x equals half times the log base 4 of x. So once again, we're taking the log base 4 of x and then multiplying all the outputs by a half, causing a vertical compression by a factor of 2, or a vertical compression by a factor of a half. I've seen them both said. All right, so but again, I'm not doing all that. We're just going to do the same thing I've been doing at each of these. Domains all real, all positive numbers, not all reals, all positive numbers. The range is all reals. And the asymptote's still the y-axis, right? X equals 0. So again, the y-axis, x equals 0, I'm going to dash that, right? That's an asymptote. And then I'm plugging in powers of 4, so say 1 and 4. Right? And then put in a quarter if you want, or 16, or 1/16, or whatever. Now the log of 1 is 0, times a half would still be 0, so you still got 1, 0 on here. And then the log base 4 of 4 is 1, times a half would be a half. Right? So here's 1, and there's a half for the output. You have the point 4 comma 1/2. So it still looks like an increasing function, an increasing logarithmic function that has the y-axis as an asymptote. So something like this. Again, this might not be perfect, but it'll have that general shape, that general look. And that's all we're asked to do. Right. Okay. All right, so now we're finally getting into some examples with multiple transformations. Again, if you were doing transformations. So 9 is, f of x equals 5 times the log of x plus 2. Now remember, when there's no base on the log, on the log, it's base 10. So if I was doing transformations, I would start with log of x, move everything left 2, right? Replace x with x plus 2 and move it left 2, and then do a vertical stretch by a factor of 5, multiply the y coordinates by 5. But again, I'm not doing that. So remember here, the expression inside the logarithm has to be positive. I'm solving this inequality. X plus 2 has to be greater than 0, meaning that x has to be greater than negative 2. So there's my domain. It's all the values greater than negative 2. Right? So everything from negative 2 to infinity, but not including negative 2. Range is still all real numbers for all of these logarithmic functions. And now this time the vertical asymptote would be at x equals negative 2. So here's negative 2. And there's the asymptote. Now, what I would like to plug in is values that make x plus 2 equal either 1 or x plus 2 equal to 5, or sorry, 10. Ew. All right, this is base 10, sorry. So I want powers of 10 in here, or x plus 2 equal to 100, or x plus 2 equal to 1/10th, 100th, whatever. So here, when is x plus 2 equal to 1? When x equals negative 1. All right. So I'm going to plug in negative 1 for x. When is x plus 2 equal to 10? When x equals 8. So I'm also going to plug in 8, right? And that should be enough, right? Those will be 2 points. Now when I plug in negative 1 for x, you get the log of 1, which is 0, times 5 would still be 0. So negative 1 zeros on this graph. And then when you plug in 8, 8 plus 2 is 10. The log of 10 is 1, times 5 is 5. Right, you get an output of 5. 8, 5 would be on this graph. So it's clearly increasing and has an asymptote of x equals negative 2. So something like this. Right? Again, something of that shape. Might not be perfect. Right? Now, where does it cross the y-axis? You plug in 0 for x. Whatever the log of 2 times 5 is, right? 5 times the log of 2. But you'd have to punch a calculator in there for that. I don't know that off the top of my head. Yeah, but this is all I'm doing. Just graphing 2 points in an asymptote. Alright, so another one involving the log base 10. We have 3 times the log base 10 of x minus 2, and then plus 1. So again, if I were graphing this with transformations, I'd start with the log of x, multiply everything by 3, then move everything to the right 2, and then up 1. Right. But like I've been saying, I'm not going to do that, right? So x minus 2 needs to be positive. X needs to be greater than 2 then. So the domain of this function is all values greater than 2, right? So from 2 to infinity, not including 2. The range is all real numbers, as always, for these logarithms. And the vertical asymptote is going to be at x equals 2 then. So here's x equals 2. Put an asymptote there, a nice dashed vertical line. The graph won't touch that. Now, again, I'm plugging in values of x so that my number inside the logarithm is a power of 10. So when is x minus 2 equal to 1? When is x minus 2 equal to 10, 100, 1,000, 1/10th, whatever? But again, I really only need 2 points. So when is x minus 2 equal to 1? When x equals 3. Now when I plug in 3 for x, you get the log of 1, which is 0. Then times 3 is 0, plus 1 is 1. Right, so the point 3, 1 would be on this graph. And then when is x minus 2 equal to 10? When x equals 12. So 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry about the spacing is terrible. This is a terrible hand drawing. If you have graph paper, that would make things a lot easier. But if I plug in 12, 12 minus 2 is 10, the log of 10 is 1, 1 times 3 is 3, plus 1 is 4. right? You get an output of 4. The point 12, 4. And I'll label this one 12, 4. That should be on the graph, right? Here's 3, 1, 12, 4. And you can plot other points if you wish. But again, we have a clearly increasing function that has x equals 2 as a vertical asymptote. And there's the rough sketch of that graph, which is all we're asked to make. And again, if you want to go to Desmos and check it out, be my guest. All right, so this one, f of x equals the log base 10 of negative x, right? This would be log of x, but reflected across the y-axis, right? X is replaced by negative x, if you were doing transformations. All right, so once again, I'm going to do the usual stuff. This negative x needs to be positive. Dividing by negative 1 flips the symbol, so x needs to be less than 0 this time. All right, so the domain for this function is all values less than 0, so everything from negative infinity up to 0. And the range is all real numbers, as usual. And the asymptote is the x equals 0 line, or the y-axis. So again, I'll dash on the y-axis here. That's an asymptote. And then I'm just going to plug in, negative 1 to get the log of 1, which would be 0. So negative 1, 0 would be on this graph. And then negative 10. And again, this is a terrible hand drawing. But if I plug in negative 10, this becomes positive 10, and the log of 10 is 1. So negative 10, 1 would be on the graph. And now we look like we have a decreasing function, right? As I move to the right, the points are going down, with this, y-axis as an asymptote. Something like this. Maybe a little curvier out here, but something like this. Right. Great. Now the next one is just like the previous one, but you have a times negative 1 outside, negative log of negative x. That would reflect it across the x-axis afterwards, right? Replacing x with negative x reflects log of x across the y-axis, and then multiplying the whole thing by negative 1 reflects it across the x-axis. But again, I'm doing the same stuff. So once again, this negative x needs to be positive, meaning that x has to be a negative number. So the domain is all negative numbers. So from negative infinity to 0, not including 0. The range is all reals. The asymptote's the y-axis, x equals 0. And I'm going to plug in the same two numbers I did as in example 11. Negative 1 and negative 10. All right. So here's negative 1. Negative 10. Now the log of 1, right, when I replace x with negative 1, this is the log of 1 is 0, and then times negative 1 would still be 0. So you have negative 1, 0. And then plugging in negative 10 for x, this becomes the log of 10, which is 1, but then you got a minus in front. This becomes minus 1 for the output. So negative 10, negative 1. And you see I have an increasing function now. Graph's going up as I move from left to right, with this y-axis as an asymptote. So something like that. Something like that for the graph of it. Alright. It's got a few more of these, and you may have noticed I'm doing the same thing every single time. So here f of x equals negative 2 times the log base 3 of x plus 4, and then plus 5 after, right? So remember the domain, I just focus on the expression inside the logarithm. So this x plus 4 must be positive, meaning that x must be greater than negative 4. So the domain of this function is everything from negative 4 to infinity, not including negative 4. The range is all positive, all real numbers. Sorry, all real numbers. The vertical asymptote is the line x equals negative 4. So here's negative 4 on the x-axis. I'll put a vertical asymptote there. And now I'm just going to plug in values so I get powers of 3. So x plus 4 is some power of 3, right? So when is x plus 4 equal to 1? When is x plus 4 equal to 3 or 9 or 27 or 1/3 or 1/9 or 1/27, whatever? So here x would have to be negative 3. Right, so I'm going to plug in negative 3, and then here x would be negative 1. Alright, so when I plug in negative 3 for x, you get log of 1, which is 0, then times negative 2 is still 0, and then plus 5 is 5. So negative 3, 5 would be on the graph. And then when I plug in negative 1 for x, negative 1 plus 4 is 3, the log of base 3 of 3 is 1, 1 times negative 2 is negative 2, plus 5 is 3. So negative 1, 3 is on the graph. So clearly we have a decreasing function with this asymptote at x equals negative 4. So the graph should look something like this. Now it eventually will hit the x-axis. It's going down forever, and it's going up forever, to the right of that asymptote, but not actually touching the asymptote. Alright. Next. Alright, so this is the first one we've seen with a natural logarithm. Remember, this ln means log base e, and remember e is about 2.718, right? About 2.7. So keep that in mind. So again, you can do transformations, take the natural log of x and then move it to the right 1 and then up 3, right? Because you got the plus 3 after, or before, but it's outside. But I'm doing the same thing I've been doing. This x minus 1, this expression inside the logarithm, has to be positive. So x minus 1 has to be greater than 0. Adding 1, x has to be greater than 1. Right, so the domain of this function is all the numbers greater than 1. Right. Range is all real numbers. And the vertical asymptote then would be at x equals 1. So there's x equals 1. Make a nice little vertical asymptote there, dashed line. And then I'm going to plug in values of x so that we get powers of e in here. So like, when is x minus 1 equal to 1? When is x minus 1 equal to e? When is x minus 1 equal to e squared, e cubed, or 1 over e squared, whatever. But really I only want 2 of them. So one of them is when x equals 2. Right, now when x equals 2, 2 minus 1 is 1. The log of 1 is 0. Plus 3 is 3. Right, the output would be 3. So 2, 3 would be on this graph. And then when is x minus 1 equal to e? When x equals e plus 1. Now e plus 1 would be about 3.7. So somewhere between 3 and 4. So let's say here that's e plus 1, right, about 3.7. And when you plug in e plus 1, you get the natural log of e, which is 1, plus 3 is 4. Right? The output would be 4. E plus 1, comma 4. And it's definitely an increasing function, this, with this asymptote at x equals 1. So it looks something like this, right? Something like that, like we've been seeing. Alright, and I got just one final one here. I'm doing the same thing every time. Domain, range, asymptote, find a couple points and make a sketch. So here I have h of x equals negative 1/2 times the natural log of x plus 1, then minus 3 afterwards. So first, the domain. This expression inside the logarithm has to be positive. So x plus 1 has to be positive, meaning x has to be greater than negative 1. Alright, so the domain of this function is, I can only plug in numbers greater than negative 1. So from negative 1 to infinity, not including negative 1. Range is all real numbers for all these logarithmic functions. And of course, the domain, so the asymptote should be simple. The vertical asymptote will be at x equals negative 1. So here's -1 on the x-axis. I make a vertical asymptote. Alright, and then now I'm going to try to find values of x that I can plug in so that the number inside the logarithm is a power of e. So when is x plus 1 equal to 1? Well, that's when x equals 0. And when is x plus 1 equal to e? That's when x equals, e minus 1. And you could do e squared, e cubed, any power of e you want. Alright, so x equals 0 is going to be on there, and then e minus 1 would be about 1.7. So here's 1, here's 2. E minus 1 is about here, about 1.7, so closer to 2 than it is to 1. Now when I plug in 0, you get, natural log of 1, which is 0, times -½ would be 0, and then minus 3, the output would be -3. So 0, -3 is on the graph. Then when I plug in e minus 1, you get the natural log of e, which is 1, times -½ would be -½, minus 3 would be -3.5. Alright, so -7 halves, right, -3.5. So e minus 1, -3.5, there's the output, there's that point. And so it looks like a decreasing function, with this asymptote at x equals -1 like this, going through these points. And there's a rough sketch of the graph of that. And that's it. I mean, that's a lot of examples, but so I did the same thing every time. What's the domain? What's the range? And if you know the domain, you know where the vertical asymptote's going to be. And then just pay attention to the base of the logarithm and plug in values of x that'll make the expression inside that logarithm equal to some power of that base. And that'll make it easier to calculate outputs. And once you've got a couple points, at least 2, you should be able to, end the asymptote. You should be able to make a rough sketch of these by hand. And of course, if you want to, you can always double check them, with the Desmos site, Desmos calculator. Great. Alright, so I'm hoping that watching me go through these 15 examples here helps you in some way when you're asked to graph a logarithmic function on your own. And thank you very much for watching.